Today we are going to see triple products of vectors. The first type of triple products is triple scalar product, and this is the definition. The triple scalar product of three vectors a, b and c in that order is denoted by this notation. The list is enclosed within square brackets, and this is the definition. It is the dot product of a and b cross c. Note carefully that because the outer product is dot product or scalar product, so it is a scalar. Next we have some properties of triple scalar product, and the first one is this: a dot b cross c equals b dot c cross a, which equals c dot a cross b. In other words, if we maintain the cyclic permutation of this list of vectors, then their triple scalar product remains unchanged. And by cyclic permutation we mean that this cyclic arrangement remains the same. After A, B comes, after B, C comes, and after C again A comes. So no matter which one you start with, here you have started with A, so then after that B will come followed by C. But if you start with B, then you will go this way, B, C, A, whereas if you start with C, it will go like this, C, A, B. The proof of this, of course, can be found in any vector algebra book. As we said already, we are not really going to see the proofs in this algebra part. In the vector calculus part, we are going to do everything in detail. And from that, we next note this. We can write a dot b cross c as c dot a cross b by that property we saw just now. However, we already know that the scalar product of two vectors is commutative. So in place of this, we can also write this a cross b dot c. So you see that we have got back the original order, not just the cyclic order that's maintained throughout, but the original order where it starts with a. We started like this ABC, we still have ABC, but now we seem to have changed the positions of dot and cross. Dot comes here, cross comes here. So in a triple scalar product, you can actually interchange the dot and the cross without changing the value of the triple scalar product. Next, number 2. The triple scalar product of a, b and c is 0 if and only if the vectors are all non-zero and they are coplanar. It turns out that this is the case, or at least one of them is the zero vector. And this just means in particular that the triple scalar product is 0 if any two of these vectors are the same. This follows from this fact. You figure out how. The third one is very interesting. The triple scalar product is positive if they form a right-handed set of vectors. And the triple scalar product is negative if the set is left-handed. Next, number 4. I, j and k form a standard basis. And say the three vectors a1, a2 and a3 have been expressed as linear combinations of these basis vectors like this. Lambda 1i plus mu1j plus mu1k is a1. Similarly, the coefficients for a2 come with 2 as suffix to distinguish them from these ones. And the coefficients of a3, by coefficients I of course mean the scalars, they come with the suffix 3. Then the triple scalar product of a1, a2 and a3 is given by this determinant, where the first row has the coefficients of a1, the second one has those of a2 and the third one has those of a3. Unlike the determinant expression for the vector product of two vectors, which is only a notation and a memory aid, this is a legitimate determinant because here we only have real numbers. We no longer have I, j and k. And next we have triple vector product, and this is the definition. The triple vector product of three vectors given in a particular order a, b and c is defined to be this. So you can see that it's just like triple scalar product. The only difference is that There we had a dot here, here we have a cross. And because of that, it's a vector. That one was a scalar. No special notation, however, is given for this one, unlike what we have for the triple scalar product. No box, nothing, it's just written like this. Only one property of the triple vector product is given, which is this. We already know that the vector product of B and C is perpendicular to both B and C, and that is why the triple vector product A cross B cross C has to lie in the same plane as the two vectors B and C, and that is why it will be a linear combination of them. That means there will exist some scalars lambda and mu for which the triple vector product will be lambda b plus mu c, and actually this is how the combination looks really. Lambda and mu are not just some scalars that have to exist, but in fact lambda is a dot c and mu is minus a dot b. All these things can be proved, of course. How do you remember this? This is something that we will use often. To remember this, you can see this pattern that first you write A dot C. You take the scalar product of A with the further vector, okay, not the near one, and then multiply B with that, and then you take the scalar product of A and B, and with that you multiply C. There is a minus in between. Note one more thing carefully, that this is actually a scalar because it's scalar product. Similarly, this one is the scalar. Let's see an example, example 1.9, where we have to expand this expression which involves four vectors A cross B dot C cross D in terms of scalar products. You can see that it's ultimately a scalar because this is one vector and this is one vector whose scalar product we are actually considering. So in the solution, the very first step may be a bit confusing at first, but you don't try to see how this comes from this one, although that's what happened, but still you try to see how this one is equal to this. What are you looking at here? This is actually a triple scalar product of three vectors A, B and C cross D. And the property that we saw there allows us to interchange the positions of dot and cross. So the cross goes there and the dot comes here. That way we get this. So that means this is really equal to this. And then this is where you use that expansion that we saw just now. B cross C cross D, this is a triple vector product. So this will be equal to B dot DC minus B dot C D. Outside we have A dot. And then you use the linearity properties of your ordinary dot product, that means scalar product. Note carefully that when you take the product of A and this vector is actually C multiplied by the scalar B dot D. So that B dot D stays separately and we take the scalar product of A and C. Whether you write this one first or that one first, it does not matter because these two things are real numbers. Just like that, minus A dot D times B dot C. So this is how we have expanded this in terms of only scalar products. And that's all we have on vector algebra in this book. We did not really, of course, see many things in details. For example, whatever we saw today was just information. But you can look in any vector algebra book which focuses solely on vector algebra, and there you will find proofs of all these things. And that's not our aim. Our aim is to just assimilate these things in one place so that we can use them. Next week we are going to start vector calculus, where the first thing is the derivative of a vector valued function of a scalar variable. And this idea, once we get the definition, This idea will then help us to define the velocity and acceleration of a particle moving in 3 dimensions. And then of course that's the beginning of mechanics.